base E and natural logarithms. This is going to be our last video in exponential and logarithmic functions and equations chapter 7 in current numbering system. So, what is base E? Let's start with what E is, right? Oops, sorry. Select the right thing. Now, what is E? So, E is called the natural base. Okay? The reasons why it's called the natural base and the origins of E and where that number comes from are beyond the scope of this course. But what you need to know, first of all, is that it is an irrational number. It's a constant. It's like pi or the square root of 2 or anything like that. It is irrational. So irrational, in case you don't remember, means that it doesn't mean that it's angry and upset. It means that it is a non-ending, non-repeating decimal. Okay, so E equals 2.71828, etc. Oftentimes you will see it rounded to 2.718. That's going to be one of your most common roundings. Now, most scientific calculators these days have an E button somewhere on the calculator. They'll either have just a straight up E button where if you push it and then push enter, it'll give you this decimal. A lot of times they'll also have an E to the X, E to the something button. Now, what I want to caution you strongly, is it's very possible, depending on what your calculator is, you're going to also have a button that's E. That's an E. That's a cool looking E. Totally a mistake. An EE button. This is not the same as that E. This is a scientific notation button, and so be aware of that. Okay, so in fact, one of the calculators I was looking at just the other day, I think it was the Texas Instruments TI-83 or 84, maybe something like that. It had both of these buttons, which can be kind of confusing. So you'll want to figure out where those buttons are. One of them is going to be E to the something. The other one is just going to be E by itself. So make sure you find those on your calculator. Now, if you want to find the log base E, so log base E, it has a special notation. It is notated as LN. Now, you're also going to have an LN button on your calculator. I saw one the other day where it's LN with both capitals, which is a little bit weird because you don't see it that way written very often. But I think that was also on the TI-83 or something like that. But it'll be either capital LN or lowercase ln, but that is almost definitely there. You may have to push second and then the common log button, but it'll be there somewhere. If it has a common log, just a log log button, it almost definitely has an LN button as well. Okay, so just real quickly, let's look at writing something in logarithmic form. So if we have E to the X equals 32. So we put the base down in the log. So this will be log base E. But remember we just said that log base E is abbreviated to LN of 32 equals the exponent, so X. So let's look at another example real quick. Let us write 4 times the natural log of 24 minus the natural log of 12 as a single logarithm. Okay, so first of all, I forgot that I changed this problem when I did it. When I did it live the other day, that kind of works out ugly. So erase it. Hope you're taking notes in pencil. Usually that's a live class only thing, but you're welcome. You got a new experience. So it's actually going to be 4 times the natural log of 144. That's going to work out much prettier. Okay, so we end up with, first of all, we've got a lot of things going on right here. So we can get these numbers to be the same. You can see why we changed the numbers. So this would be, we can also bring this into the inside. So let's do some manipulating. So this can be the natural log of 12 squared, because that's 144. And then that can be raised to the 4th. So that we're bringing that inside because of the power rule, right? So let's not do too many things in one step. So let's just do minus the natural log of 12 now. All right, so now we've got the quotient rule because we've got common bases, this log minus that log. So we're going to kind of jump on down and end up with the natural log of 12 to the 8th over 12. So that's this one over that one, because 2 times 4 is 8, right? So if we use exponent rules and we subtract the exponents, we subtract 8 minus 1, right? We end up with the natural log of 12 to the 7th. Now, a lot of times you'll see this cleaned up one step further by putting this guy back out front. So our final answer on this problem is going to be 7 times the natural log of 12. That's all she wrote. You could, if you want a decimal approximation for that, you could plug that in on the calculator and see what happens. But that is a good enough answer. Let's do another one. This time we're going to be solving for x. So we've got 4 times e to the negative 2x minus 5 equals 3. So we're going to solve for x. So we want to do some isolation here, okay? So we're going to isolate this e to the whatever x, in this case negative 2x. So we're going to add 5 to both sides, right? Plus 5 plus 5. Leaving us with 4 times e to the negative 2x equals 8. Then we're going to divide both sides by 4. Those cancel, leaving us with e to the negative 2x equals 2. All right, so just like we did before with the common log, we can do the same idea, but take the natural log of both sides. So we can take the natural log of this side and the natural log of that side. Okay, so when we do that, we can pull this exponent out to the front. So we've got negative 2x times the natural log of e equals the natural log of 2, right? Natural log of e to the 1 equals e, so that cancels and just goes to 1. So, and we can also, while we're doing things, we can divide off that negative 2. Divide off that negative 2. So the natural log of 2 divided by negative 2, you can just chuck that all in your calculator, and you end up with x being approximately equal to negative 35 hundredths. And that, my friends, is all she wrote on that problem. Just to get some more experience with logarithmic equations, let's do one more. And let's go with 3. Let's try that with a better color. You can't see that. So 3 times the natural log of 4x equals 24. Now we're going to simplify that, we're going to divide both sides by 3 to get rid of that guy, right? Because it's multiplied onto all that mess. And we end up with the natural log of 4x equals 24 divided by 3 is 8. All right, now this is where we do something. We're going to add one more piece to clean this up. This is going to be kind of a little bit brain bendy here. All right. So what we can do to get at this inside, we could switch this to logarithmic form, excuse me, to exponential form, and that would be one way to look at it. And it actually ends up kind of basically being the same math on this problem, but because of inequalities, it's better to think about it this way. So what we're actually going to do is we're going to take and we're going to use the property of equality, and we're going to have both sides raised e to that power. Okay, so e to the natural log of 4x and e to the 8th. All right, so when we have e to the natural log, e to the natural log of x, that equals x, equals whatever's inside of there. Okay, so there's your new pseudo property. It's actually kind of taking some other properties and sticking them together. All right, but it's gonna be good to remember this. E to the ln equals whatever's on the inside, right? So in this case, that would be 4x, right? So we have 4x equals e to the 8th, which in this case would be the same as if we just simply wrote this in exponential form. Doing it this way will help keep these signs straight if you're doing it with an inequality. So there is that. Now, the last thing we need to do is divide both sides by 4 because it's multiplied onto the x. So x equals e to the 8th over 4, which is approximately equal to 745 and 24 hundredths. So there is your final answer in exact form and in an approximate form. All right, let's see if we can jump over and look at one last thing. And we talked about compound interest before. Just an aside real quick, because there's a different type of compound interest. We talked about interest compounded annually, compounded monthly, but sometimes you will see interest that is compounded continuously. Okay, so that's another way of looking at things. Another type of problem you might see, and it's really a nice U-O-U-S-L-Y, continuously. It's a nice problem because it uses a simpler formula. It uses a simpler version of this formula. It has an exponential form, which is A equals P. These are the same as they were before. The amount after T years, P is principal, times E, that is the same E we're talking about, to the RT, rate times time. Or you could write this in logarithmic form. Sometimes that's useful. Okay, so it would be the natural log of A over P equals rate times time. All right, so on a compounded continuously problem, one of these two formulas will get you there in a trick. Let's do one example using compounded continuously. All right, here it is. So if you invest $3,500 into an account which earns 15% per year compounded continuously. All right, that's an important word, right? How much money will you have after 10 years? If it said compounded annually or compounded monthly or some other version therein, you would have to use our longer version of this formula. But since it says compounded continuously, we're looking for the A at the end, so we're going to use the exponential. A equals P times E to the RT. You could probably make some kind of rap out of that or something. All right, so in this particular problem, our P, that's not very easy to see. Let's try again. Our P equals 3,500. Our R equals 15%, which would equal 0.15 as a decimal. And our T equals 10. So this is really, really straightforward. We just plug in and chug out these numbers. So A equals 3,500 times E to the 1500ths times 10. So when we multiply these out, you end up with 3,500 E to the 1.5. Then when you stick that thing into your calculator, you end up with A is approximately equal to 1,500. Whoa, that went wild on me, huh? 1,500, $15,685.91. Quite a bit of money in 10 years for just sticking something in there and waiting. All right, that is absolutely it for this chapter. You guys have a great time, and we will see you on the flip side. Adios.